Okay, for the last scribblecast of this module, number 2, we're going to look at another person who played with gases. His name was John Dalton. So we'll look at his law of partial pressures, and we'll also just briefly mention and discuss the kinetic molecular theory of gases. Okay, so Dalton, look at that chap. He looks quite good, better than that last Avogadro guy. Anyway, Dalton, he's been known for a number of different things in chemistry. Look him up too. He's quite well known for lots of things. Atomic theory was one thing he messed around with. But he also looked at gases. And his law says that for a mixture of gases in a container, the total pressure exerted is the sum of the partial pressures of the gases. In other words, if I have two gases in a container, so here I have a container, and maybe I have a red gas, and maybe I have a green gas. Sorry, that looks a bit Christmassy. But the green gas doesn't affect the red gas. So the pressure of this total in this container, to find that, all I have to do is find the pressure of the red ones, and then find the pressure of the green ones, and add them up. So the partial pressure of, like it says here, the partial pressure is the pressure that the gas would exert if it were all alone in the container. So for example, here I've got a nice little diagram, but it's showing me, here I have two gases, and then here I have a third gas. Notice that I have the same volume in each case, and I'm assuming I have the same temperature. I don't know if it, oh yeah, it says that, 20, 20, 20. Same temperature all the way around. In this one, I have hydrogen gas, and I measure the pressure to be 2.4 atmospheres. Here I've got helium gas measured at 6 atmospheres. Now if I take the hydrogen out of this one, and I dump it into this one, that's what this third one is indicating. Notice that the pressure, I have hydrogen, I have helium, the total pressure on that system is measured as 8.4, but when I look at it, I get that 8.4 simply by finding the pressure of hydrogen, find the pressure of helium, and adding them up. So that is Dalton's law, that the total pressure in any system is equal to find the pressure of each individual gas and then add them up. So of course, if I only have two gases, it'd be P1 plus P2. If I had 4 gases, I'd add all 4 of them up. So here's a question that I can use to do that. I'll maybe show at the end, I'll show another way of doing this as well, which might be a little bit easier, but we'll do it according to what Dalton was talking about. So here I've got some helium gas, I've got some neon gas, I have them in a 2.5 liter container at a constant temperature. So the question is calculate the total pressure. But to do that, we're going to calculate the partial pressure of each gas at STP, and then I'll calculate once I know each one of them, then I'll calculate the total pressure. So for the first one, let's do helium first. So this would be my helium side, this would be my neon side. So helium, I want to figure out the pressure, so I'm going to solve the equation for P, so nRT over V. So the pressure is equal to the number of moles, 0.25 moles, times my universal gas constant, liter kilopascal per Kelvin mole, times the temperature. The temperature at STP is 273.15 Kelvin, and divide that by the volume. Volume is 2.50 liters. So my moles cancel, my kelvins cancel, my liters cancel. I'm left with kilopascals. So the pressure in here, bringing out my calculator, will be 0.25 times the universal gas constant times 273.15 divided by 2.5. So the pressure in this one is 227. Now I need how many sig figs? Just 2. Oh darn. So we'll call that, this is kilopascals. I'm running out of room. I need 2 sig figs there, so I'll write it as 230 kilopascals. Okay, so that is the pressure in the container due to helium. Now we'll do neon. I could do the same formula, nRT over V. I'm just going to plug the numbers in my calculator because they're all very similar, and won't write it down there, but typically I would write them all down. Okay, how many moles of this one do we have? 0.5. 0.5 times universal gas constant times 273.15 and divided by the same volume, 2.5, equals, okay, and this one comes out to 454.19. Rounding that to 2 sig figs, I'd call it 450 kilopascals. So the pressure in that container due to neon is 450, pressure due to helium 230 kilopascals. So Dalton said to find the pressure of the whole system, the pressure total of that system, just add the two together. So I'd add 230 kilopascals plus 450 kilopascals, which would be equal to about 680 kilopascals. So that would be the total pressure on the system. Okay. Now another way I could have done that is, since the effect of them are the same, and since they're both at the same temperature and pressure, or the same temperature and same volume, I could have really just added the moles together. So I could have added the moles of helium plus the moles of neon. So 0.25 plus 0.5 was 0.75, and then use this as my moles in my PV equals nRT. If you do that, you'll see that you come up with the same number. But that's because it was at the same temperature and the same volume. Let's try another similar kind of question using the same formula. Sample oxygen saturated at 30. Total pressure, the total pressure of both water and oxygen. So it looks like I've got oxygen in a tank and I've got water vapor in a tank. So I've got two together. So if I was writing my Dalton formula, it'd be pressure total is equal to the pressure due to oxygen plus the pressure due to water. So that would be my formula. But here they say the total pressure of both water and the oxygen is 753. So in this question, they actually gave me the total pressure. Now, what else do they say? If the vapor pressure of water is 31.824, so pressure due to water, 31.824 torr, what is the partial pressure of the oxygen gas? So here I've got a simple, I guess, algebraic kind of thing. To determine the pressure due to oxygen, I'll just take the total that I had and subtract the pressure due to water vapor. So when I subtract those two with my calculator, 753 minus 31.824 equals 721. So the pressure due to oxygen would be 721 torr. Now I put those in there just in case I needed to convert, but they didn't ask me to convert in the question, so I'll leave it as 721 torr. Notice that I didn't, like for sig figs, I didn't put any decimal places here. The rule when you're adding or subtracting numbers is to go with the least number of decimal places. Here I've got 3, here I don't have any decimal places, so in my answer I can't put any decimal places. So 721 would be the answer for that one. Okay, I've enjoyed looking at these laws, and I'd encourage you to do some research in your textbook and online, and just learn maybe a little bit more about the people and learn more about the significance of the laws that they came up with. All of these laws were based on experimental evidence that Boyle and Charles Avogadro, Dalton, and others, that they gained using experiments. Now, since these people, and maybe during as well, some people try to theoretically look at the behavior of gases and to try and explain those. So I guess it would be this theory would go in conjunction with the experimental evidence that Boyle, Charles, and others came up with. So somebody came up with a theory that tried to explain the behavior of ideal gases, and that theory is known as the kinetic molecular theory of gases. It states that all matter is made up of tiny particles, which are all in constant motion. So tiny particles, molecules, motion, kinetic. So the name itself sort of says what it's talking about. So it's saying that if I have a gas, that gases are made of tiny particles which are always in motion. They have some postulates or some assumptions that they use to sort of help identify or help explain their theory. And these are that all gases consist of atoms or molecules, and that the volume of just the molecules of the gas is negligible. In other words, if I have a container and it's filled with a gas, or it has a gas in it, I'm not sure how you would say that it wouldn't be filled, because even if you had 2 or 3 molecules of gas, they are in constant motion, they'd be filling up the container. Anyway, but if you were to take all of those particles and slow them down so that you could actually take a volume of just how much they are, that volume would be negligible when it's compared with the total volume of the container. Also, particles are constant random motion. Particles do not attract or repel each other. And as part of that one, so they're always in motion, so they're moving this way and moving that way, moving all over. And when they hit each other, their collisions are elastic. And so, I don't know if elastic is the right word, but when they hit, they don't affect the other one. They won't change the energy of the other molecule. So they don't attract or repel each other, and the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. So, and this one here sounds very similar to Charles's law, that the temperature affects the volume, or here it's saying that it affects the energy. But when we're looking at the Kelvin temperature as being a main thing that affects those gas particles. Let's maybe look at temperature just a little bit more. Here I've got a container, and at whatever temperature this is, doesn't matter, these particles of gas would be moving at a certain speed. If I increase the temperature, the speed or the kinetic energy of those molecules, I'm going to write that, kinetic energy of molecules will also increase. So if I raise the temperature, the speed of those molecules will be going faster. Now, let's take a look at that in relation to pressure. So if I increase the temperature of a container, what effect does that have on pressure? Just think about that for a sec. If I increase the temperature, what's that going to do to the pressure? Of course, you're probably saying that the pressure will also increase. And certainly that's something that those who studied gases experimentally would also say. you probably have an experimental evidence. And if you want to try this, well, maybe not, but because they tell you not to do it. But if you were to take an aerosol can and throw it in a fire, you would experience this. The temperature of the gases inside that aerosol can increase, therefore the pressure increases, and the pressure would get to a certain point where it would have to be released, and that's where the fireworks or the excitement would start. But it's based on this kinetic molecular theory. If I increase the temperature, the molecules are moving around faster. Therefore, if they're moving around faster, their effect on the container will also be affected. Okay, I paused to clean up my diagram a little bit. Let's finally look at the relationship then between temperature and volume. Say, for instance, that this black line here was a piston of some sort that could move up or it could move down. If I take a look at the temperature, and if I increase the temperature, so I add some heat to this, as we've just looked at, the kinetic energy of those molecules inside will increase, so they're moving all around, and the pressure then on the outside, or the pressure on the container, will also increase. So, I guess the question I'd have is which way do you think that piston would move, and when would it move? Okay? So if I increase the temperature, the molecules moving around faster and faster, the pressure on the outside of the container will increase. Therefore, logically, it would make sense that that piston would get pushed out, or it would get pushed up. And it would get pushed up only when the pressure that's being exerted down is equal or greater or is equal or less than the pressure that's being pushed up. So as soon as I can get the pressure inside here that's greater than the pressure being pushed down, then that piston would move up. Okay, so those are, I guess, some examples of how we can use the kinetic molecular theory to help us explain the behavior of gases. So we've looked at, in this section, Dalton's Law, which says that the total pressure of any system is equal to the sum of all of the gases that are inside that system. And we also looked at the kinetic molecular theory, which talks about how molecules of gases are moving and the behaviors that might suggest.